Right, so here we go with A2 Physics from CCEA, and this is Fields and Their Applications from June 2016. Question 3. Figure 3.1 shows the variation in voltage across the capacitor with time as the capacitor discharges through a fixed resistance. The capacitor is fully charged at time equal to 0 seconds. Draw a circuit diagram to show how the capacitor may be charged quickly and discharged slowly. So we've got very specific: charging quickly, discharging slowly. So we need a very particular circuit. So what we're going to need for quickly is for there to be no resistance in the charging side of the circuit, and the resistance only turns up then on the discharging side. So you want to sort of have two sides to your circuit. So you're going to want to have some kind of power supply connected to a switch point. That will go around and connect to your capacitor through a switch. So if we throw the switch over here, we can get the capacitor to charge. What we then want to do is have a second switch point where we can throw it over to discharge, and that side of the circuit needs to have some resistance in it. And the idea then is that the capacitor can be flipped over from position A to position B, charging very quickly with no resistance at A and discharging slowly through a resistor here at position B. Now you're going to need to also figure out what's happening with the voltage, so you're going to need to be able to measure the voltage across the capacitor. So you've got a circuit with no resistance, which current will flow quickly in this one, and it'll charge very quickly on this side. You flip this switch over to here and you'll have a circuit with resistance, so the discharge will be much slower. Using your circuit in 1, describe a procedure that would enable you or enable someone to record the data required to plot the graph of figure 3.1. So figure 3.1, remember, is this voltage over time graph, so that tells us immediately what we're needing to measure. So you would charge the system and then switch it to discharge, and the idea then is that you would record that voltage regularly. And if you look back at the graph, you can see here in the graph that the whole thing's done in 150 odd seconds. Okay, so you're going to need to be recording the voltage at very regular intervals over short gaps, like maybe 10 seconds, 20 seconds, in order to get enough points to plot this graph. So flip it to the charge, flip it back to discharge, and start your stopwatch and record the voltage every 10 seconds or so over a period of, you can see there, 3 or 4 minutes. Okay. Part B then says, deduce the time constant for the capacitor resistor circuit from 3.1. So the easiest way to think of this is to say that at t equal to 1 time constant, what we find is that V will equal V0 times 0.37, so the 37% value is what it will fall to during 1 time constant. So you can see here that it starts at 18. We just need to find 37% of 18 and then figure out where that is on this scale. So when I do that, I get that the voltage will fall to 6.66 volts. So that's going to be about there. So we need to take that across to our graph. Do it with a ruler, obviously, on my really rough measurement here. And it's somewhere between about 55 and 60. And obviously the more accurately you do it, the better a result you're going to get. Okay then, so If the fixed resistor has a value of 123 kiloohms and the capacitor is made up of 3 equal valued capacitors in series, determine the capacitance of each capacitor. So we know that the time constant equals the product of R and C, and we've just been given here the value of R. So C is going to be that time constant over R. So that's going to be like 57 over 123 times 10 to the 3, because it was given here in kiloohms. You need to just watch your units there. So I'm getting this value. Obviously, if your time constant from your graph is different, you'll get a slightly different value, but it should be similar in size to this. And that's the 3 capacitors in series, so we need to figure out what that means about each one. And remember, when capacitors are in parallel, they add together, but when they're in series, they use the 1 over formula. And that means that 3 in series would have a value which is 1/3 of this value. So if we just call this C for the series bit, then we can say that 1 over C for the series is going to equal 1 over C plus 1 over C plus 1 over C. Okay, which means that C will equal CS over 3, which is that value of 0.0000463 over 3. And I get 0.000154 for that. And this value is going to be totally based on what you get for this time constant. And the mark scheme, I think, is coming across and suggesting that it's 1.42 times 10 to the minus 3 farads. Hold on, that's wrong. That would have to be 10 to the minus 4, so the mark scheme's wrong. Okay, so that's similar to my value. And it will be different if this number is different. Question 4. Wedding corsages, lapel badges, photographs, etc. may be secured in position using thin permanent magnets, and Table 4.1 provides manufacturer's information on how the magnetic flux density and magnet strength vary with distance from a magnet. The data is for a neodymium magnet of diameter 10 millimeters and thickness 1 millimeter. So we've got these values for how far you are from the magnet, what magnetic flux density you get at various distances, and how much force it pulls with at those distances. It says determine the magnetic flux at the face of a neodymium magnet of diameter 10 millimeters and thickness 1. So at the face will be at distance 0. So what they're basically asking you to do is do a calculation here about magnetic fields coming out of this area at this value to get a phi value. Okay, so we have an equation that says that phi equals BA, so we know that. So we pick the B value and the A value and we do a calculation. So we need to multiply by A here, but we need to watch because the information they've given us is in millimeters. Now A is going to be pi r squared, so if diameter is 10 millimeter, then we can remind ourselves that if A is pi r squared, then we're talking about pi times like 5 times 10 to the minus 3 for millimeters, and then squaring that. So that's what needs to go in here. And so again, there's always a unit thing here. So 129 times 10 to the minus 3 for milli times pi times 5 millimeters squared. Okay, so we're converting to meters here, 5 times 10 to the minus 3. So millis here, millis here. We need to be careful about our units. And that's the sort of value coming out of my calculator. So I'm going to put that down as 1.01 times 10 to the minus 5 of a Weber. Part B, when a copper rod is placed 1 centimeter from the circular pole of the neodymium disc magnet, only 1.3 centimeters of the length of the rod is within the magnetic field, and they've highlighted that there. So this is the amount of rod that's in the field, this bit here. Use the information in both Table 4.1 and Figure 4.1 to calculate the force experienced by the copper rod when a potential difference of 15 volts is momentarily applied between its ends. The rod has a resistance of 2.4 times 10 to the minus 4 ohms. So, several things going on here. First, you would use Ohm's law to get a current, because we're going to do an F equals BIL calculation. So I is going to be V over R. You can do this in one go. You don't necessarily have to work out I. You can put V over R into your equation. The L here is going to be the amount in the field, so that's that value. And the B is going to come from the section of the table that tells us what B is 1 centimeter out. So we go back to your table, we look at the 1 centimeter value for B, we take I from V over R, and we take L from the diagram, and we just substitute into that. So that should be easy enough. So looking back at the table, the B at 10 millimeters, which is the 1 centimeter we're interested in, is 10 milliteslas. L we've got from the diagram, and I is going to be just V over R, these numbers that we've already got. Okay, so F is going to be BIL. Which is the same as B times V over R times L. And for us, that's going to be the 10 millitesla times the 15 over 2.4 times 10 to the minus 4 times the L, which is 1.3 times 10 to the minus 2 for centimeters. So watch your units, get everything in the standard unit. B must be in teslas, I must be in amps, and the L must be in meters. And so we've done all that. Just feed that through your calculator. And I get 8.125 newtons for that, so I'm going to put that down as 8.1 of a newton. In what direction will the force be experienced by the copper rod act if the top of the rod was connected to the positive terminal of the 15 volt supply? So if it's plus up at this end, then that means that I is running down like that. And we know that B is coming out this way because that's in the diagram. B is like that, I is like that, and we now need to do left-hand rule for that. So pointing finger straight across this way, second finger down like that, and when you get your left hand into that position, you should find your thumb is pointing straight up out of the page, and so that is what we need to do. So establish a diagram. There's 3 marks for this. So establish a diagram and make it clear that you're using Fleming's left-hand rule with the current flowing down the page. B pointing to the right gives us a thumb position that's pointing out of the page. And so that's what we want to be able to say. And we want to be able to explain why, because it does say explain your answer. So Fleming's left-hand rule with these 2 in place gives us a thumb pointing out of the page. You want to be able to explain that. So elaborate a little bit, but you want to be able to say that it's out of the page and that you're applying Fleming's left-hand rule for the B and I that you have demonstrated.